Johnson is like first year. This is my own back. It's like
yeah, master. So I'm doing
It's probably the slide. Yeah, it's all right there. Yeah, it's more there. Yeah, back corner. Yeah. Don't forget your coin. Actually, it's actually got a. The wheels just come off. Too much. Yeah, I don't like
Hello. Sorry, I'm here late.
It's all right.
No. I'm not quite sure how long I'm going to.
Good evening, guys. Thank you so much for coming to our talk. We've got Sir Martyn with us today. I'll just give a short introduction for him and then I'll let him get right to it. So Professor Sir Martyn studied at King's College, Cambridge in 1969 and a PhD in 1973 under the supervision of J.J. Turner on the matrix isolation of large molecules. In 1972, he was appointed Research and Senior Research Officer in the Department of Inorganic Chemistry of the University of Newcastle upon Tyne. In 1979, he then moved to a lectureship in the Department of Chemistry at the University of Nottingham. He was awarded CBE in 2008 for services to science and knighted in 2015 for services to chemical sciences. He was made honorary member of the Chemical Society of Ethiopia in 2008 and foreign member of the Russian Academy of Sciences in 2011, and honorary fellow of the Chinese Chemical Society in 2015. His research interests are focused on supercritical fluids, continuous reactions, and their applications in green and sustainable chemistry. Since 2008, him and his colleagues have collaborated with video maker Brady Haran to make chemistry videos for the YouTube channel Periodic Videos.
So, first question is, can you hear me at the back? Second question, there are 2 empty seats near the front. So if you can't see properly, please feel that you can come and sit in these empty seats. Come on. Anyway, you know the title of my talk, and if I talk too quietly and you can't hear, just wave your hand. And I want to dedicate this talk in memory of my father, who was an undergraduate here at UCL. I'm ashamed to say in physics rather than chemistry. And he was an undergraduate, he had started in 1927. So that's nearly 97 years ago.
It was joint between chemistry and physics, so he would have probably attended some of these meetings in those days. It only split later.
Yeah. And where you see the historian Andrea knows these things better than me. Anyway, the aim of my lecture is to show how I became fascinated with supercritical fluids and how they led me to green chemistry. And the key point I want to try and show you is the role of chance. Unexpected things that happened that actually got me along the way. And I'm often asked, well, not often, from time to time, which year in the history of chemistry I think is the most exciting. And I usually say 1869, for the obvious reason that Mendeleev published the periodic table, and you can see this one at the back. But the other one, which is you probably don't know, is that the chemist Thomas Andrews gave his so-called Beckerian lecture. And the reason why gave is in inverted commas is because he published the lecture, but because it was rather late in the year, they forgot to give him the opportunity to actually speak it. One imagines that in the old days, everything was done really well, but even in the old days, they muddled things up. So this is Thomas Andrews. You can see here. He was at Queen's University, Belfast. This is his paper called On the Continuity of the Gaseous and Liquid States of Matter. And this is a rather nice picture of his apparatus. I won't use the laser pointer or I might irradiate the people behind the bar. And what he did was to study the behavior of high pressure carbon dioxide. And this is a three-dimensional model with temperature, pressure, and volume, which was made at Queen's University, Belfast. And the last time I saw it, it had lost its base. And this is a photograph that hangs in my office at Nottingham. And what he did was to produce the phase diagram, rather like this, where you have pressure on this axis, temperature here, and solid, liquid, and vapor. And the line between the vapor, that's the gas, and the liquid ends in the so-called critical point. And up here, above the critical point, is the so-called supercritical region. And if you haven't seen it, it's really quite fun to see what happens if you heat up a gas and liquid in equilibrium till you reach the critical point. And here, if I can get it to work, I have a video, and this is a closed cell with a liquid here and its vapor above it. And I will try and show you what happens. Oops, sorry. What happens if we heat it. So if you start heating it, it begins to boil, you'll see bubbles. And the liquid expands because it's getting hotter, and the gas gets denser because it can't escape. So the density of the two get the same, and the meniscus disappears. And then if you cool it down, it separates again in a sort of huge storm like that. And I think this is really beautiful. And I used to keep this in my office, this demonstration, till I ran out of space. And I would show it to people who came to as prospective members of our research group. And if they got excited, I knew they were suitable to work with me. And if they looked bored, I would tell them to work with Professor Y down the corridor. Then a few years later, in 1880, the Scottish chemists Hannay and Hogarth did a second very important paper called On the Solubility of Solids and Gases. And they showed that you could dissolve solids in a highly compressed gas, a supercritical fluid. And they dissolved, I think it was cobalt chloride in supercritical ethanol. I got into terrible trouble in Scotland when I said that it wasn't surprising that in Scotland they used ethanol. But so I won't say that now. And I still find it amazing that you can dissolve solid materials in a highly compressed gas. And this is used for decaffeinating coffee. Most of you are probably too young to be interested in decaffeinated coffee, but the usual way of removing caffeine from coffee, and this is caffeine, it's about the amount of coffee from 300 cups of English coffee, 100 cups of Italian coffee. And the traditional way of decaffeinating is with dry cleaning fluid, which leaves interesting residues in the coffee beans. But you can use supercritical CO2 to extract the caffeine from coffee beans. And if you're interested in supercritical fluids, this book by Mark McHugh and Val Krukonis is a really good introduction. It's quite old now. It's the only textbook I know that has jokes in it. And anyway, this is a picture of the decaffeination plant being built. This is the pressure vessel, and here is a worker for scale. So you can see this is a serious piece of kit. And in terms of chemical engineering, it's quite clever. You have this huge vessel here full of coffee beans, and you pump CO2 round, and the CO2 then goes into the second column where you spray water, and caffeine is much more soluble than water than it is in CO2. So at the bottom, you get a solution of caffeine coming out, and you have decaffeinated coffee beans. So in terms of economics, it's great. Your coffee beans become more valuable because they're decaffeinated and you can sell them to old people. And you have a solution of caffeine that you can sell to Coca-Cola. So nothing is wasted. So this comes down to me. And in 1984, when the story starts, that's 39 years ago, I was an inorganic chemist, and I was studying short-lived molecules and using liquefied noble gases. This is argon, krypton, xenon, which were discovered here in UCL. And the these liquids, gases, are really good for infrared spectroscopy. IR light is absorbed by the vibration of molecules or atoms in the molecule. These noble gases have only one atom in the molecule, so they cannot vibrate. And therefore, you get totally transparent solvent. And what we did was that we exploited the fact that these liquids have very short liquid range between their freezing point and boiling point, but you can extend the liquid range by increasing the pressure. So if you go up to 20 bar, then you get an overlapping liquid ranges going from down here to nearly minus 180 up to 40, over 40 to minus 40 degrees. And the problem was that we needed to go to higher pressures to get close to room temperature. And then the first chance event happened. There used to be an airline called TWA, Trans World Airlines, and they had a special offer that if you paid the full price to fly to America, you could then have 8 internal flights in America at $25 each. This was not some sort of cut price airline. You got the full food and everything else. And I went to America with one of my PhD students for collaborative experiments. And Barry, the student who went with me, was determined to use all 8 of his 3 flights, and we didn't need them all for our project. So he took a side trip to Boulder, Colorado, to where there was a physical chemist called Veronica Vida. And Barry saw a high pressure cell on her desk. And he, without asking me, invited her to come to Nottingham and to bring the cell with her. The poor woman who's standing there, there's an empty seat near the front. Come and have a seat. No, you'll have to come round here. Come round this side. So, come round the front. Okay. So, here's the cell. She brought the cell to Nottingham and left it behind for us to use. An ideal visitor. And she also only stayed a short time. And so I wanted to dissolve something up in the gas to see if it was true. So I didn't photograph the original experiment, but this is a recreation we did later. And I remembered as an undergraduate, I had used an extraordinarily brightly colored blue molecule called diazulene. I have no idea what it's actually used for, but it made such a mess. It was terrible to clear up when I was an undergraduate. And here you can see there is diazulene dissolved actually in supercritical ethane or liquid ethane. And as you heat it up, you can see that the meniscus disappears and nothing precipitates. And I fell in love. So then I got a PhD student here, Steve Howdle, who is now head of the School of Chemistry at Nottingham, and therefore my boss. And here you can see him using one of Veronica's cell. And what we realized is that hydrogen gas is not very soluble in ordinary liquids, but hydrogen gas is just a gas like supercritical fluid. So supercritical fluid and hydrogen mixed together completely. So you get a much higher concentration of gas, hydrogen, in a supercritical fluid than you do in an ordinary solvent. This slide is designed for little children, so you can see blue plus yellow is green, just to demonstrate the mixing. And so we used this reaction, this high concentration of hydrogen, to make an unusual hydrogen complex of manganese. I got very excited about it in the time, but it really was not of enormous significance. Now, you can't see from the photo of Steve that he's a very big guy, and we had very expensive windows for the high pressure. And in one morning, he smashed 2 windows, which blew the entire budget for his project for a year to replace the windows. And this is a 50p piece, just to give you the scale. So we had a real problem. And then the chance event number 2 happened, that Don Braben, who was director of the so-called BP Venture Research Unit, came to lunch in Nottingham. And this was a fund from BP that funded exciting research. And the purpose of his visit was to get him to fund a big project with a professor. And so we had lunch, me, Don, and the professor. And the professor made a big pitch, which I thought was really good and exciting. And Don Braben said it wasn't interesting. So what happened was I got really angry. And so I jumped up and started saying how exciting supercritical fluids were. And Don said, that sounds interesting, write me a proposal. So yeah, this is Don Braben. I should say that he was, after he left BP, he was a visiting professor here at UCL. And he gave me a grant for called Supercritical Fluids and Environment for Reaction Chemistry. At the time he gave it, it was the biggest grant that any member of staff had ever had in the chemistry department. And what was interesting to them, perhaps the members of staff, that his principle was that he gave money to people he liked. And he did not have any sort of peer review. He didn't ask other people what they thought. Anyway, so as you probably know, that chemists are meant to make molecules, and I've always been very bad at it. So I saw an opportunity to build a machine to make molecules. And I thought that what I would like to do was to make an ethene complex, because at the time, my German friend Friedrich Grevels, who was a wonderful synthetic chemist, had been defeated by making a chromium complex. So I came up with the idea that I would have a pump with supercritical ethene in it. I would pump it through a cell which I could irradiate with UV light to promote a reaction, use infrared spectroscopy to monitor it. And here I could isolate the product by releasing the pressure quickly, so the supercritical fluid turned to a gas and the product would precipitate. Once it was a solid, it would be stable. And the critical temperature of ethene is 9.2 degrees, which even with a bad heating in Nottingham is above room temperature. in winter. And so this is the apparatus. Here is the pump. The reactant dissolves here. You irradiate it with UV light, the infrared spectrometer, and you release the pressure, and the product is isolated there. And here's the product. It wasn't totally pure, it was 85% pure. And this is the hand in the glove box of my student, James Bannister. So I was really excited. We had a machine that would make molecules. And just to show you, this is how I feel one should do synthetic chemistry. You turn a handle and the product comes out. And it works. So this led me to the area of green chemistry. Green chemistry is now become really quite popular. It is cleaner approaches to making chemicals and materials. But this was just starting in the early 1990s. And one of the areas was cleaner solvents. And supercritical fluids have been highlighted as one particular area of solvents. And the idea is you do something in the lab and get it into industry. And in 1994, I was lucky to get a fellowship from the EPSRC and the Royal Academy of Engineering with so-called Clean Technology Fellowship. And I was the first person to be awarded one of these fellowships. It paid my salary for 5 years, and in principle, I didn't have to teach. So in fact, I actually did more teaching when I got the fellowship than before, but don't tell anybody. And then came the third chance event. There was an article in the journal New Scientist. How many of you read New Scientist? I read it more or less since I was a teenager. And the article, which appeared on the 6th of August, 1994, was called Solvents Get the Big Squeeze. And by a journalist called David Bradley. And I was a bit offended. It was about supercritical fluids and talked about different people's work. And I felt didn't really give enough justice to the wonderful research that I was doing. But what it did do, it had this quotation of what's called vending machine chemistry. It didn't have the picture. It said the chemist will simply press a button and the machine will add the appropriate reagents to supercritical CO2 and pump the mixture into the reactor. And then about 3 months after the article was published, quite late one evening at 9:30, I was phoned at home by this gentleman, Thomas Swan, who was the owner of a company called Thomas Swan & Co. in Consett in County Durham. For those of you who don't know UK geography, Consett is in the northeast of England. And at the time, this was the second largest privately owned chemical company in the UK. And he phoned me late at night and said he'd read this article, he wanted to collaborate. And after a lot of discussion, we decided to collaborate on supercritical hydrogenation, adding hydrogen to organic compounds. And the apparatus, which in chemical and engineering terms was not very sophisticated, is that you take the substrate, what you want to react, and the hydrogen and supercritical CO2, and actually mix them together. Originally, we had a mechanical mixer, and then we passed the substrate over a catalyst and reactant turned to product, and here you release the pressure, and the product went one way and CO2 went the other. And Javadar, who's sitting here, at the time was a postdoc in my group and was one of the people who worked on this. And this shows slightly after Javed's time, my colleague Pete Licence, who's now director of our sustainable chemistry lab. Here is the mixer. There is the reactor, which is about the size of my hand, or my finger. And then the product comes out here. It's a continuous reactor. And together with Thomas Swan, we scaled it up. And this is a plant, the plant. You can see with the worker to scale. This is the reactor. And it was 1,000 tons a year, and it opened in July 2002. And for those of you interested, this is the reaction hydrogenating a molecule called isoprene to make this one, which is the rather unromantic name of TMCH, trimethyl cyclohexanone. And it is, this is the very first bottle of product which is labeled batch 1. And I got really excited. I sat in my office all morning looking at this bottle. And then one of the research group came and said they needed it, and I never saw it again.
Oh.
But unfortunately, just after the plant started, the price of energy suddenly shot up, and the cost of compressing the CO2 became high, and the process stopped being economic. So although technically the plant was really successful, it was not economically sustainable. So this brings me on to the next way the work developed, was to build automated reactors. And this is a slightly old diagram, but the idea is you have the same basic reactor, but you have a sampling loop that works automatically, and the result goes to a gas chromatograph that can analyze the product, and all the analysis is stored on the computer, and everything, the temperature, the pressure, the flow rate, can be stored, changed by the computer. So the machine runs by itself and stores the data without the operator having to sit there to change things. So this is an example of the sort of results hydrogenating this molecule called furfural, and using a copper chromite catalyst. And this shows the composition of what's coming out, and this shows the temperature. And each of these data points is a different experiment that was done automatically. And you can see what is unusual in this catalyst is that when you get to temperature here, intermediate temperature, you get a lot of this product. But if you go to a higher temperature, you get that one. So you have one catalyst that can make two products. And what I found exciting this is that it opened up the possibility of making a chemical vending machine. Because if you think about it, if you have two different reactors that can either be cold or each with a catalyst, and each reactor can either be cold, in intermediate temperature, or hot, you can have lots of different combinations. This one can be hot, that can be cold, they can both be intermediate temperatures, so on. So that there are lots of possibilities. And so here you can say, with the same molecule furfural, you could, by varying the temperature, get a whole series up to 5 different products. without doing anything except asking the computer to change the temperatures of the reactors. So I got quite excited. And since then, we have gone on to do what are so-called self-optimizing reactors, where you take the online analysis and then you feed it back to the computer via an algorithm. And the algorithm decides how it can change the reaction conditions, temperature, pressure, whatever, to optimize the amount of product that you have. And you can see we've published a lot of papers since then. So this is fully automated. The students can be thinking about the chemistry and don't have to be worrying about the details of running the apparatus. So this brings me to the fourth chance event, that which by chance happened on the 1st of April, April Fool's Day. I bumped into my colleague Mike George in the corridor, and he said, we're going to make anti-malarial drugs together. And so what he was thinking was that we would look at reactions of so-called singlet oxygen. I hope you will remember from your chemistry, first year chemistry course, that oxygen, O2, normally has unpaired electrons, but with a photosensitizer, you can cause these electrons to pair for a short time, and the oxygen suddenly becomes much more reactive. And you can use it to make all sorts of molecules, including antimalarial drugs. And Mike's idea was really to take the same principle we use with hydrogen, but to get a high concentration of oxygen in supercritical CO2, but with a bonus that supercritical CO2 is non-flammable, it doesn't burn. And you can imagine if you're doing chemical reaction with oxygen and an organic solvent, you're worried all the time that suddenly it will go bang. So if you have a solvent that can't burn, you immediately feel more relaxed. So the first experiment we tried was the reaction of this molecule here, alpha-terpenine, which was shown about the year I was born, that it reacted with singlet oxygen to make ascaridole, which was used to be used for treating worms in people's stomachs or digestive system. And so we used a photosensitizer, which had a lot of fluorine in it so that it would dissolve in CO2. And the reason for using CO2, it's non-flammable. You can separate the product by releasing the pressure, and it's miscible with gaseous oxygen. So this is then postdoc Rich Bourne, who's now very successful professor in Leeds. And we originally did the reaction in this little batch cell, and we got out this amount of product, it's about 30 micrograms, and there's a 2p piece to give you a scale. And then we converted this into a continuous process and made a really big scale up of 3,000 times and made 96 milliliters of product in about 8 hours. And the ascaridole should be colorless, but this has still got the photosensitizer dissolved in it. And after that, we built a variety of continuous reactors and did a lot of different reactions of singlet oxygen. And then this led to an interest in the anti-malarial drug artemisinin. So those of you who are from China will know that the Chinese scientist, Dr. Yu Tu, won the Nobel Prize in 2015 for the identification of artemisinin, which traditionally has been isolated from a plant called Artemisia. But the problem is that you plant the plant, wait for it to grow, you harvest it, and then you isolate it, and this takes months. And there's a problem that artemisinin is too complicated a molecule for organic chemists to make at a reasonable cost. But there is a semi-synthetic process that was developed in the United States and by the pharmaceutical company Sanofi, their name was short on the bottom, where they use genetically modified yeast to do fermentation to make this molecule here, artemisinic acid, which then uses chemistry, including singlet oxygen, to make artemisinin. And that takes weeks rather than months. And this is their pilot plant. They've now got to manufacturing scale. So you can see the light shining, making singlet oxygen. And they used dichlorophane, chlorinated solvent, as for the process. And if you think about this from the point of view of green chemistry, photochemistry is a really good, clean way of making the things, but dichloromethane is a bad solvent from the point of view of toxicity. It uses a toxic acid, trifluoroacetic acid. You don't recycle the catalyst, and you need more solvents to clean things up. And it's a batch process, not continuous. So you do one pot, and then you do another pot, and so on. So the German chemist Seeberger came up with a continuous process. You can see here his apparatus. We use toluene rather than dichloromethane, and got quite good conversion and yield. But we decided we would try and do it in supercritical CO2. And this was done by PhD student Jess Bellamy and postdocs Zach Amara and Red Horvath. And so we got really quite good conversion yield. And what was for us quite an exciting thing is that we had a combined catalyst that had both the photo catalyst absorbed onto an acid catalyst. So it had two functions. It was both an acid catalyst and a photosensitizer. And you can see this is the acid catalyst called amylist. We mix it with the photosensitizer, and you get something that looks like miniature garden peas because the protonation changes the color. And it worked well, but then Ralph went to University of Durham and used equipment in Andy Beebe's lab to measure the rate of reaction in a mixture of ethanol and water. And normally people don't use singlet oxygen in water because it's deactivated very quickly. The electrons unpair. But surprisingly, we found that the reaction was faster in a mixture of ethanol and water than it was in pure ethanol. And so we did the reaction in ethanol and water. And the exciting thing at the end, when we started evaporating off the ethanol, out came absolutely pure artemisinin. We took one of these crystals, and then an hour and a half had the crystal structure. It was already known the crystal structure, but it shows that it was pure. And so you have the basis of a really nice process where you put in the dihydroartemisinic acid and oxygen, you do the photochemistry, you distill off some of the ethanol, you filter off the product, and then you recycle the photocatalyst, the acid, and everything else. And so you're just putting in the renewable materials and light, and out comes pure artemisinin. And this was published in Nature Chemistry now 8 years ago. So the problem then is we got really excited about doing photochemistry in conventional solvents, and we wanted to communicate this to chemical industry. And we came to the conclusion that research groups needed to combine together because no single research group was really powerful enough to reach out to industry. So Mike George led a big project, which has just finished, called Photoelectro, which combined chemists from 3 universities, Bristol, Southampton, Nottingham, both engineers and chemists, and a large number of companies. And it had big objectives, giving access to chemists to underexploited reactions, integrating these reactions into multi-step processes, and designing user-friendly photochemical and electrochemical reactors. So time is short, so I will just tell you about one reactor that we developed, which is called a vortex reactor. And this is really quite unusual. It consists of a glass test tube, if you like, a container, and inside is a stirrer which is flat and completely smooth. Normally a stirrer is like a propeller, but this one is smooth and it rotates very fast. And solution goes down there and goes up the outside. And then you can have lights on the inside, outside to irradiate it. So you have the lights here and this stirrer in the middle. And the important thing is that as this rotates, it creates what are called Taylor vortices, which mix up the solution. So all the molecules get next to the glass so they can be irradiated by light very efficiently. So here you can see some vortices, and this is what is called computational fluid dynamics, where you can actually compute how the vortices are made as a function of the solvent, the size of the gap, and so on. And here you can see it actually running, and you can see these vortices going round. And this has turned out to be really very successful. And you can do all sorts of reactions. I've just shown here doing it in the vortex, doing artemisinin, where you don't even need, in this particular version, to use oxygen, because as this spins round, it sucks in air from the room. So it just produces it as you want. And you can get to 2 stages where you add the acid with the second vortex reactor. And so we've got to a scale of about 200 grams a day, which for academic lab is quite nice. And this is a special slide for American audience to put in a scale that they can understand. We have a small reactor, which is the size of an AFC cup, which which will make about 1 kilo a day, and the bigger one, which fits nicely into KFC bucket, which will make about 11 kilos a day for an appropriate reactor. So, the reason why this is important is because the pharmaceutical industry is changing. And personalized medicine means they need more products, but in smaller quantities. And the reason is because as you do genomic analysis, you realize for the same disease, what will treat one person won't work on somebody else. So the other person needs a different drug. And so we need improved engineering to make the manufacturing of medicines much more agile. You can change the products you're making much more quickly. So really what's needed is together, and by together I mean all chemists and chemical engineers need to work together to realize a more sustainable chemical industry that is powered by light. So we use light in innovative reactors so we can make new molecules. So, and our vision is that you will have a pool, if you like, of reactors that can do photochemistry, electrochemistry, thermal chemistry, and you can put these together into chains so that you can make different products just by assembling them in different ways. So I just want to thank all of my students, co-workers, colleagues, collaborators, including Jared, but particularly Mike George, who now leads our research group. I'm just a minor member, and Steve Howdle, who started the supercritical work. And I would particularly want to thank our technicians who make a lot of our equipment. And those of you sitting near the front will see that I'm wearing a badge saying, I love technicians. This is really important. And I also wanted to thank the agencies, companies that have funded the research, especially the EPSRC. So, and finally, to remind you, some memory of my father, you can see sitting there. And I'm pleased to say that my father came to the last lecture that I gave here at UCL, which I think was in 1994, on celebrating the centenary of the discovery of argon. Thank you.
Does anyone have any questions?
Of course, they must have.
Yeah, do you have any questions? Yeah.
An observation and a question. The observation very quickly. Some in the audience might be interested to know that the swan of whom you show the photograph is a past president of the Society of Chemical Industry, and that the business, as in the swan company, is still run by his son, Harris. The question then is
just interrupt you a moment. Harry Swan is now chair of the trustees of the SCI. So
he is indeed, yeah.
Anyway, go on, your question.
I could have a long conversation with you about that. The question is in the extraction of caffeine by the supercritical fluid method, is the carbon dioxide recycled, or does the pressure have to be raised?
No, it is recycled round and round, and you extract the caffeine largely with water, though you will release some CO2 in the water, and of course you have to get the beans out of the vessel, so some CO2 will come out with that as well. So the answer is that there is not 100% recycling of the CO2, but there is a big recycle. But the other reason why it's profitable is that decaffeinated coffee beans are far more valuable than most chemicals. So the price per kilo is pretty high compared to a kilo of specialty chemicals.
And this is connected, I suspect. I'm a planetary scientist that's recently been a very speculative paper. That early Mars being cooled with a thick carbon dioxide atmosphere would have had supercritical carbon dioxide at the surface.
Yeah.
And the scientists were speculating this is very reactive stuff, would have interesting effects on Martian surface chemistry. Is that plausible?
Yes, I thought you were going to ask about Venus, which has very high pressure and high temperature CO2, with just more than a dash of sulfuric acid. So I think CO2 is a pretty inert material because it is a thermodynamic sink. And sunlight on Mars is much weaker than sunlight here on Earth because it's a lot further away from the sun. So I would have thought it might have had some modest effect. But probably what would be more important is the water in the CO2 giving acid solution. Yeah.
To dissolve the supercritical CO2, I think you mentioned that you dissolved it in a fluorinated solvent, and I was wondering why that is.
No. What I said, well, I may not have spoken clearly. I said that the fluorinated photosensitizer dissolves better in CO2 than an ordinary. And there are two reasons for it. First of all, in general, fluorinated compounds have weaker intermolecular interactions than non-fluorinated compounds. This is why fluorinated coating on a frying pan is so good for the food not sticking. But so you have weaker interactions to break and to dissolve the material, but also that fluorinated compounds, fluorine interacts with the quadrupole of CO2, and you get a positive interaction with the solvent, which also helps it to dissolve. It's a very good question. Thank you.
I noticed that you use many high pressure reactors, which is relatively dangerous, especially for us when we start with risk assessment. So how do you manage the safe, especially when scaling up?
Well, so if you didn't hear the question at the back, is how can one be safe with doing these experiments at high pressure? Well, the answer is that, first of all, it's all on a relatively small scale. And the bigger you make a pressure vessel, potentially the greater danger. And the other point is that you have to do careful risk assessments. And you have to train your students how to do how to work safely with high pressures. And the pressures are high, but they're not enormously high. They are perhaps usually not higher than 200 atmospheres. Whereas there are some people that do experiments at 20,000 atmospheres or even thousands of atmospheres. So I think the answer is you have to be careful and make sure that things are set up so if they do, something does break, they are contained and it doesn't matter.
Thank you for a wonderful talk, Martyn, and always good to go down memory lane. I really enjoyed that. Some of this audience will be aware of your YouTube
videos. And so I wonder if, have you got a couple of favorites from the YouTube videos?
Well, I have lots of favorites. My all-time favorite is a video, the first video we made about element 108. For those of you who are not familiar with the videos, we began by making one video about each of the 118 elements on the periodic table. We did this in a period of 5 weeks. So I made the very arrogant decision there was no time to look anything up. And when we got to element 108, I did not realize the camera was running. And I said, I know nothing about Hassian. Shall we make something up? And that's the opening of the video. And what I then said was that it was in the same group as iron, ruthenium, and osmium, so that you could predict what the properties might be like based on the others. And I ended up by saying that if it was more stable, it would have made a great addition to my PhD thesis. But subsequently, we then went to Darmstadt, where Hassian was synthesized. It's a synthetic element. And I learned quite a lot more about it. And so, but that's my all-time favorite. Our most popular video in terms of number of views, I'm ashamed to say, is putting a McDonald's cheeseburger into concentrated hydrochloric acid on the rather weak excuse that you have hydrochloric acid in your stomach. And that was just past 20 million views. And our second most popular video in terms of views, which has got to 11.6 million, is about chemistry of plutonium. And I think the color of plutonium-3 in solution, sort of gorgeous purple color, is probably my favorite color of any chemical. We've never so far videoed metallic plutonium, and I'm still finding somewhere where they will let us video metallic plutonium. Our most popular video in terms of likes is a video of what is called the Pythagoras cup, which is a cup which, when you fill it, automatically empties if you're too greedy with the amounts you've got, which has, I think, 7.5 million views, but 178,000 likes. But I'm always most excited about the latest video we've made. And our latest video was about the quantum dots of the Nobel Prize. And the one before that was about thulium, which burns amazingly well. To give a, if you could afford it, thulium fireworks would be great. So,
you mentioned that you got into researching, how did you get into researching
well, ever since my PhD, which was a long time ago, involved studying coordinatively unsaturated nickel carbonyl compounds, which were created at very low temperature by freezing the metal carbonyl in very dilute solution in solid argon, and then shining UV light to dissociate the carbonyl to make the coordinatively unsaturated species, which, because it was frozen at 20 degrees absolute, couldn't recombine. So I've really been involved in photochemistry in one way or another since I was quite small. Well, not small, but scientifically small.
Right, thank you all so much. Really exciting lecture, but May I ask you, could you use the same method for tea, to decaffeinate tea? Because it's not beans, it's.
Yeah,
You don't have
the
to.
answer is you can use CO2 to decaffeinate tea. The problem is, well, the reason why it works so well with green coffee beans is that it removes caffeine, but doesn't remove anything else. If you decaffeinate tea, it removes other flavour components as well. And you have to put those components back in again, or the tea tastes a bit flat. So it isn't used as widely for decaffeinating tea. You can also use it to remove nicotine from cigarettes. But why people should want to smoke cigarettes without nicotine, I'm not sure. You get all the health problems with none of the benefits. Yeah.
So it poses an interesting point. Is that how they get the nicotine for vaping?
I have no idea.
Some form of solvent extraction, I guess, unless it's.
I would have thought that CO2 would probably be too expensive a way of extracting it for vaping. After all, if you bear in mind all the other things they put in vapes, they probably don't worry about solvent residues.
Well, don't worry about the purity, but that would add to the attractions.
Yeah. A little louder.
Sorry.
Yeah, mostly out of 316 stainless steel. When we've been working with supercritical water, which is much higher temperature, 300, the critical temperature is 374 centigrade. We have used an alloy called Hustalloy, and on occasions we've used titanium as well. But most of it's with 316 stainless steel. The only problem is that you can't use chlorinated solvents because you can get stress corrosion cracking. It can break. Well, yeah, we use swage lock, and at the time that Java worked in our group, the group had two halves, and one half of the group used metric swage lock, and the other half used imperial swage lock because they didn't want other people pinching their units. Any more questions? Yeah.
The Hannay in 1880, is that the Hannay who subsequently tried to synthesize diamond?
It's an interesting question. Perhaps Andreas.
Sorry, I didn't, what was the
The 1880 Hannay supercritical stuff, was he the Hannay who subsequently tried to synthesize diamond?
I mean, so many people tried to synthesize diamond, it may well be constructed in the end of the 19th century. But, you know, it was certainly, sorry, the name will come to me in a second.
Right.
It's quite.
So, any more questions?
Can I ask you a quick one? You've been involved in Africa quite a bit. So have you been out there, or where you and what's the sort of contribution of Nottingham? Because I did notice that Robert Boyer was awarded from Nottingham with someone who's worked with you.
Yeah, I mentioned that my father was a physicist. My grandfather was a physicist, and both of my parents-in-law were physicists, and my wife's grandfather. So it's not surprising that my son became a physicist. And he announced that nobody with intelligence could do a PhD. And then he, after 18 months working in the industry, he said he was bored and was going to go and teach physics in a high school in rural Ethiopia. So he went off to Ethiopia, and a year later, my wife and I went to visit him, and I was asked to give a talk at his school about green chemistry. And it was turned out to be the first talk about green chemistry in the country. And there were so many people that Simon had to lock the door of the room. And there were people, it's ground floor room, there were people looking in the window from outside. I've often been in rooms where the people in the lecture theatre have been looking out through the window, but this was the only time that I've had people looking in. And the teacher said it was really interesting and we ought to go and visit the university in Addis Ababa. So we went to visit it when we went back to the capital, and I met a chemist there called Nigis Asfor on the stairs of the chemistry lab. And it's a long story, but we became friends. Her husband is a very distinguished botanist and has become the first African ever to be a foreign member of the Royal Society, the UK Academy of Sciences. And this summer, it's just been in July, Nigis was made an honorary fellow of the Royal Society of Chemistry and received an honorary degree from Nottingham. And Pete Licence, whose photo you saw, is an adjunct professor at Addis University and collaborates quite a lot. So, I should say that when I was after this lecture on green chemistry at Simon's School, my wife complained that my trousers looked rather short. And I said nonsense. And then the next day we were packing up to go to Addis Ababa, and Janet suddenly said, "Where are my trousers?" And it turned out that I was wearing her trousers. So the first lecture on green chemistry in Ethiopia was given by me wearing my wife's trousers.
If no one has any more questions, let's give Sir Martyn another round of applause. We have pizza and drinks in G06, and we hope you can join us. Thank you.
Stop recording itself. 没有，他这样。